Hello students and welcome to our first video of this week regarding ethers and epoxides. This chapter also has information about thiols and sulfides, and we'll talk a little bit about that, but we'll mostly not be covering that in a lot of detail. So epoxides here are highly reactive compounds that we can use in synthesis reactions to make other compounds. When you have combustion and stuff like this, epoxides are formed, which are highly reactive, and so that's one of the reasons why cigarettes are dangerous. And then thiols, these tend to have a bad smell, so for example, when a skunk sprays, the smell you're smelling is a thiol. Okay, so let's start with ethers here. Ethers are groups that include oxygen attached to two alkyl groups, so two carbon atoms. Notice that this is different from being a acyl group. Acyl groups, we'll talk about those next semester, but those are involved in ester, right, where the carbon that is attached to the oxygen is also double bonded to another oxygen. This is an ester, it's not an ether. It will behave chemically very, very differently. So we're talking here about ethers, oxygen bonded to two other carbon atoms without carbonyl next to it. Ethers are extremely common in biomolecules. We got vitamin E here with an ether in it. Fluoxetine is a antidepressant. It's called Prozac as the trade name. Or morphine here, a painkiller medication that also contains an ether. Lots and lots of ether. When it comes to ether, unfortunately with ethers, common names are extremely common. You're going to see people use common names for ethers all the time. So, for example, when we use diethyl ether in the lab, that's usually what it's called. It's called diethyl ether, or two ethyls, diethyl ether. And so it's named on the bottle with this same type of simple naming like here. And the simple naming goes, you state the kind of substituent on one side of the ether, you state the kind of substituent on the other, and then you end with the word ether. So this is an ethyl group. Ethyl, this is a methyl group. We say methyl and say ether. Here, this is a tert-butyl group. This is a methyl group, so we say tert-butyl methyl ether. People use that naming particularly for small ethers like this all the time. It's not the IUPAC systematic naming. Instead, what is done is that you look at the two groups on either side. Whichever has the largest chain, you call that the parent chain. So for example, on this side, this chain of carbon atoms is 5 carbons, which is longer than 1, and so we call it pentane. And then the smaller side, we call it an alkoxy group, and the alk is replaced with whatever this is. So since this is an ethyl group, we say this is ethoxy. And so the IUPAC name is ethoxypentane. And when it comes to ethoxy groups, these don't have any particularly high priority. They have the same priority as chloro, bromo, basically the lowest. And so these are just named as substituents. The ethoxy, methoxy, all those are named as substituents in a similar way that methyl, ethyl, bromo, chloro, and all of those types of low priority substituents would be named. So pretty simple, not very exciting here. It's just the alkoxy groups is a substituent like chloro, bromo. It's in that way. The parent chain is the longer chain. That's it. When it comes to bond angles, the bond angles are similar to that in water or alcohols. It has it's got a tetravalent type of situation with 2 bonds and 2 lone pairs. So the angle is 109.5 approximately. Of course, the lone pairs take up a little bit more room. So in water, this angle is a little bit lower at 105. For an alcohol, it's pretty close to 109.5. You've got 2 alkyl groups that can use up a little bit more room, and so it's a little bit wider than 109.5, but the bond angles are about 109.5. The oxygen is sp3 hybridized with 2 bonds and 2. The larger the alkyl group, the wider this angle will be because they get in each way, and there'll be some steric issues. Now, when it comes to their physical properties, when we covered alcohols in the last chapter, we were talking specifically about how alcohols do hydrogen bonding with one another. So they have some strong intermolecular forces. And now ethers can accept a hydrogen bond because they have an oxygen that's partially negative. They're bonded to some carbon atom that has lower electronegativity, so the electrons are being pulled towards the oxygen. So we have this partially negative oxygen atom, and so that can be attracted to the partially positive hydrogen atom on an alcohol. So we would say that ether is a hydrogen bond acceptor as opposed to a hydrogen bond donor. The alcohol can donate a hydrogen bond by by having its partially positive hydrogen attracted to a partially negative atom on a neighboring molecule. So the thing is that ethers cannot hydrogen bond with themselves. So their intermolecular forces are going to be a lot lower than those of alcohols. And so you can see the result here. Obviously, propane, this is just carbon-carbon hydrogen bonds. So there's only London dispersion forces here, London dispersion forces only. Now, an ether like this, it has polar bonds. These bonds are polar. The electrons are being pulled towards the oxygen. So it's partially negative over where the oxygen is, but it's not as nearly as polar of a bond as an OH bond. And so you can see that this has the dipole-dipole forces, but they're not particularly strong because you can see that the boiling point is actually not that much higher than that for a non-polar alkane molecule. So even though there's some polarity to this molecule, it's not really extremely polar with just the carbon-oxygen single bonds here, like this. And some of that has to do with the angle. The angle is only 109.5, so you don't have, it's not like a carbonyl where you have a oxygen sticking way out, away from everything, pulling the electrons its way. It's more like it's a kind of, in the middle, so that the net dipole is not huge. And so you can see that in terms of the boiling points, as opposed to like ethanol with hydrogen bonding, much higher boiling point. Those molecules, because of the hydrogen bonding, will attract to each other much more strong. So ethers have boiling points and intermolecular forces that are slightly slightly stronger than those for alkanes, but not by that much, not as much as you might think, given that carbon-oxygen is such a polar bond. Now, London dispersion forces are going to be important. You know that London dispersion forces, they get larger as the molecule gets larger. So we can see here when we add more carbon atoms, that has a significant effect on the boiling point, and it's because the London dispersion forces are getting larger and larger for the larger molecule. But for molecules of similar size, like these guys here, it's going to be hydrogen bonding that has the biggest impact here for ethanol, comparison of the boiling point. So ethers are very common solvents. You guys know we've already used diethyl ether very commonly. In fact, some people will just call it ether, diethyl ether. That's so commonly used as a solvent in organic chemistry. THF, we've also encountered that in the hydroboration oxidation, another common solvent. 1,4-dioxane here. It's because they have relatively low boiling points, so you can evaporate them. They're not particularly reactive. And also, they're a little bit polar, so they can dissolve a little bit polar things okay, too. So they're a good choice for solvent in cases. Metal atoms can be stabilized by accepting, basically, or being attracted here to the negative oxygen side. So again, on an ether, the oxygen side here is partially negative. Not by a whole lot, it's not a hugely polar thing, but you're going to get this attraction between a metal ion, which is positive, and the negative oxygen atoms. And so that can stabilize a metal intermediate such as a Grignard reagent. So ethers are great for stabilizing the Grignard reagent and making sure it doesn't react before we go and do our Grignard reaction. It's highly reactive with molecules like water, with protic things like water. For that reason, ethers are used to stabilize metal ions that are used for reactions, for organic reactions. And the specific types of ethers that are commonly used for alkali metals are referred to as crown ethers. And it's because they kind of look like a crown when you look at their structure here. The way they're named is in terms of the total number of atoms around the ring here. There are 12. There are 10. Let's see. There are rather 8 carbons, and there are 4 oxygens. So that's 12 atoms total. And then it says crown 4 because there are 4 oxygen atoms in the crown. And then similarly here, there's 15 total atoms in this crown ether, 10 carbons, 5 oxygens. So it's called 15 crown 5. This one has 18 atoms with 6 that are oxygen, 18 crown 6. And so having these multiple ether groups can really help to trap a metal ion in here. So the metal ion will be like right in here, and it's positive, and it's going to be attracted to all these little negative oxygens, which can help to hold that metal ion in there until it's carried over to wherever it's supposed to react. So the size of the metal, the crown ether is chosen to match the size of the metal ion of interest. So for example, the 18 crown 6 crown ether is just the right size for a potassium atom to fit right in there between the oxygen atoms. So metal ions, the thing about the metal ions is ionic compounds dissolve best in polar solvents like water, which can solvate them better and stabilize their ions. However, ions are not particularly soluble like metal ions in nonpolar solvents because there's no positive or negative part to this solvent for them to be attracted to, really. And so these are helpful to dissolve metal ions in solvents that they usually wouldn't be able to dissolve in because they will stay trapped in this ether molecule, and that ether molecule will be soluble in the solvent, and then it'll get carried around until it reaches its desired reactant molecule, and then it will be released and react. So if you take like a 16 crown or 18 crown 6 like this, and you put it in a flask with nonpolar solvent like benzene, and you put it in KF, the potassium ion will be able to separate and keep itself in the crown ether. Otherwise, the KF would not be very soluble in benzene because it's completely nonpolar. So in terms of which ether is useful for which ion, the smallest one is best for the lithium ion, the 12 crown 4. Sodium ions are larger. These are all alkali metals, group 1. So the 15 crown 5 is the right size for that one. The 18 crown 6 is the right size for the larger potassium ion. So this allows us to use metal ions in nonpolar solvents, which they would not, an ionic compound normally would not be soluble. To prepare diethyl ether, the diethyl ether is used by the acid catalyzed, or is created by the acid catalyzed dehydration of ethanol. And so the first step here is you have an acid, so you protonate the alcohol, which, as we've seen many times before, that makes it so that if a substitution reaction occurs, the leaving group will be water, which is a stable leaving group, rather than hydroxide, which is much, much less stable. So once we've protonated the alcohol, it's prepared for a SN2 reaction. In this case, this will go quite nicely because ethanol is a primary alkyl halide. And this is a weak nucleophile, weak base, another ethanol molecule. So you have an SN2 attack, the loss of the leaving group. Now your alcohol is still going to be protonated, so this oxygen now will have 3 bonds, 1 to this carbon, 1 to this carbon, and 1 to this hydrogen. So 3 bonds and 1 lone pair, not 2, because this lone pair will have made the bond to the carbon. So the last part is to get deprotonated by the alcohol or by water or something to grab the proton and then ether. So you can make simple symmetrical ethers this way. As you know, we have the attack by ethanol on ethanol. So it's a bunch of ethanol in the solution acid, and you can make an ether that way with 2 ethanol molecules essentially combining to make each of the ethyl parts on either side of the ether. Now, a superior way, though, of preparing an ether actually is the Williamson's ether synthesis. And what this involves is deprotonating the alcohol first, making it a better nucleophile, and then reacting with an alkyl halide. Of course, the halogen will be a much better leaving group than even the water that we saw last time. Halide ions are great leaving groups. So we react with sodium hydride here to deprotonate the alcohol. So we saw that in the last chapter too. You can use hydride or amide to deprotonate the alcohol. Hydride's a good choice because when it deprotonates the alcohol, it will make hydrogen gas, which will just fly away. And so since it's removed from the reaction vessel, that will push the reaction forward. It will push this forward because hydrogen's leaving. H2 leaves, and so it's going to push this equilibrium forward, deprotonating this alcohol completely. And at that point, so we got a second step here. This takes a second step. Afterwards, you're going to introduce the alkyl halide, best if it's a primary one. That way your SN2 reaction will go very well, and so you'll have an SN2 reaction with the alkyl halide, a nucleophilic attack, while the leaving group, which the halide, simultaneously leaves. And at that point now you've got an ether, and you don't have to necessarily prepare a symmetrical ether in this case. Notice on one side we've got some R group, could be anything. Then on the other side we have methyl. Or it could be ethyl if we use ethyl iodide. You have your choice there. So that's why it's a little bit better of a synthesis than the simple acid catalyzed dehydration of alcohols. So yeah, that's just what I was just saying here. Williamson ether synthesis is fine, not just for symmetrical ethers, but also for asymmetrical ones. And since this is SN2, you really want a primary or a methyl halide. You don't want a secondary because you'll start to get significant combination with E2 reactions instead. So this works best with a primary alkyl halide in the second step. So for example, if you want to make this ether MTBE, which you guys might not be as familiar with now, it was a big issue maybe like 10 years ago because it was being used as an anti-knock agent in gasoline, but they found that it makes the water, for example, a local lake, it got some MTBE in it here in the Inland Empire, and it really makes the water taste bad, even in tiny, tiny concentrations. So wherever they used to, have gasoline and people would do their jet skis and stuff, it would get in that water and really, really ruin the taste. So they had to ban MTBE. But let's say you want to synthesize MTBE. Well, you got two choices. You can start with the tert-butyl side. So you're starting with the tert-butyl side with tert-butanol, and then you can add the methyl side with methyl iodide after deprotonating the alcohol and doing the Williamson ether synthesis. The other option would be starting with the methyl side and adding the tert-butyl side, but that would not be as good because if you deprotonate this, you use the hydride, you deprotonate this, and you've got the methoxy ion. O minus. When it tries to attack here, it's going to be sterically hindered because it's a tertiary alkyl halide. So this is not the preferred way. You want to use the way that you would be reacting with methyl halide here. It would give you a much, much faster SN2 reaction. Now, way back in chapter 8, we were talking about the creation of alcohols via oxymercuration, demercuration, HGOAC2 to NABH4 here. Okay. And for this oxymercuration, demercuration, we can make alcohols from alkenes, and then we can carry forward and or likewise, if we use not water, water here, instead, if we use an alcohol, we can make an ether. It's the same reaction, same mechanism, just instead of water doing the nucleophilic attack here, it's going to be a alcohol. And we talked about that in chapter 8 as well. This is just a reminder that if you use an alcohol in the oxymercuration, demercuration, instead of instead of water, you will add OR here, instead of OH, and so this will make this an ether. And there's Markovnikov regioselectivity, so note that the OR group goes on the more substituted carbon, hydrogen on the less substituted. So that's another way to make an ether. You can do the opposite here. If you react the ether with an acid, you can separate the ether into an alcohol and an alkyl halide. So this is essentially like the opposite of the Williamson ether synthesis in a sense. And so you take an ether and you react it with a hydrohalide. And so that's going to be sufficiently acidic, very strong acid. So it's sufficiently acidic to protonate the alcohol. And so we have a proton transfer here where the proton goes in the alcohol. And this makes sense because the HX is a stronger acid than this protonated alcohol is. Right? And at that point, then the leaving group, or this methyl here, will leave. What will happen is you'll have a formation of a bond in an SN2 fashion with the halide ion, and then the electrons in the bond will be left behind here, and you'll alcohol. And so there you go. And then in addition, you can form a second alkyl halide in this fashion because you've still got the alcohol. So if you react with two equivalents of the acid, you'll have a protonation of the alcohol. Again, you can have another SN2 reaction. Now you've made another alkyl halide, and all that's left here is water. So you can go, ethers can undergo acid catalyzed here, or acid promoted rather. The acid is a reactant, catalyst. Acid reaction with acid to break the ether and make it into alkyl halide. So acidic cleavage in this way will work with HBr and HI. If the R group is tertiary, then the cleavage is going to occur by SN1 mechanism. If the R group is aryl or vinyl, you can't do the substitution. The reason why is because you'd be talking about making a very unstable aryl or vinyl carbocation, and so it's not going to happen. So yeah, you can do it with methyl, primary, tertiary. Secondary doesn't work as well. It can work, but it definitely doesn't work if your alcohol or your ether is right on a benzene ring or right on a double bond, vinyl or aryl. Back in chapter 10, we talked about how ethers can undergo autooxidation and produce a hydroperoxide. This is a very common reaction in the atmosphere, and so we can see here, and with ethers that are just sitting on the shelf, like in our shelf in the chemistry lab, we have to be a little careful because when these are just sitting there exposed to air, they will produce these unstable hydroperoxides. So our ethers in the lab, we have to replace these pretty regularly. You may remember that they were in those metal tins so that they will not be exposed to a significant amount of light to initiate a radical autooxidation. And the way that works is first we get some radical initiator. This could be anything, could be oxygen. Is when it behaves kind of like the diradical, right? Diradical, it's drawn as a diradical here. Just exposure to oxygen, especially to some other radical initiators. For example, if exposed to a peroxide, this would happen extremely quickly. But we start with a hydrogen abstraction, so the radical initiator here will form a bond with the hydrogen, and one electron will be left behind. This electron here is next to the oxygen atom. You have like this little bit of radical resonance going on, which is why this occurs. Then we have a propagation, which involves a coupling between a diradical oxygen. Now this is called a propagation because we're starting with a radical, we're ending with a radical. And it's unusual for a coupling to be a propagation, but in this case it is because it's a coupling with the oxygen diradicals that preserves a radical on this oxygen here. So we have a coupling between diradical oxygen. That leaves one radical right here. And at that point you can have a proton abstraction from a neighboring ether, and that will regenerate this ether radical and the hydroperoxide. Add these, you'll you have the ether as an intermediate getting used up and reproduced here, and also the radical that was produced as an intermediate as well. So finally, the termination is just the coupling of whatever other radicals. Add up the reaction. You start with a radical, reacts with oxygen, get this intermediate. The intermediate there is used up in the next reaction with protonated, the one with the reactant, the ether reactant molecule, basically still with a hydrogen attached. It gets deprotonated in hydroperoxide. And overall, you have just the reaction of the ether with oxygen makes the hydroperoxide. Now, we've talked now about straight chain ethers. What's going to be really important in terms, and something we've already used in the past, back when we were in Chapter 7, we talked about this again, and Chapter 8 was the cyclic ethers, in particular epoxides. So ethers can be involved in a ring structure like this, and these can involve 3 atoms, like we have here: 2 carbons, 1 oxygen; 3 carbons, 1 oxygen; 4 carbons, 1 oxygen; 5 carbons, 1. And these have their own special names, which you don't have to remember. We're going to be primarily focused on oxiranes, or also known as epoxides, because as you can see, this bond angle here is 60 degrees. This is not a good bond angle for a carbon atom. It should be close to 109.5. So this has a significant ring strain, and the ring wants to pop open, and makes it unstable, but it makes it reactive in a way that is useful to us. We can use it for SN2 reactions that produce alcohols in the. So an epoxide here can have up to 4 groups attached. Each of these carbons here have 4 bonds, so 1 to oxygen, 1 to the other carbon, and then 2 to other carbons. And so here the simplest epoxide would be the one with all hydrogen atoms there. Now, epoxides are unstable. As I said, there's a lot of ring strain in these 3-membered rings, but you can find them in nature. Here's an example: the sex pheromone of a female gypsy moth, the sex pheromone of a cockroach. Both involve these epoxides, highly reactive epoxides. When it comes to naming epoxides, they have their own special way of naming them. So the oxygen here is treated as a side group, just like you would kind of think of it the same as like we would for the other ether, right? We would call it some alkoxy, right? Methoxy, ethoxy, so forth. So you're kind of given, it's kind of like that. So the oxygen tree is a side group. You find the longest chain that has that, and you start numbering from the side that is closer. So here we're numbering left to right in terms of locants instead of right to left, because then we reach the first group here at carbon number 2 instead of carbon number 3. So in terms of the name, the parent chain here is pentane. Ane, all single bonds here. Pent, 5 carbons. On the second carbon, we have a methyl group, so we say 2-methyl. On the third carbon, we have an ethyl group, this one here, so we say 3-ethyl. And then the rest of this is just part of the parent chain. At that point, we say it's like we have two alkoxy groups, except we just call it epoxy. 2,3-epoxy, because the oxygen is attached to the second and the third carbon. Or you can name it as a substituted oxirane, but I think this is the easy preferred method. I think we should go with that. But if you name it as an oxirane, then each of these are just substituents. So we're saying 2 ethyls, 2,2-diethyl, 3,3-dimethyl, calling the oxirane the parent chain. So oxygen is 1, number 2, number 3. I think that's kind of odd and different. This kind of follows our naming convention. I think this is the superior way of naming these epoxides. Now, we learned in the previous chapters, in the alkene chapter, chapter 8, that if you react an alkene with a peroxy acid, you will get an epoxide, and then we can use those epoxides for SN2 reactions to produce products. The common, now you'll sometimes see this often written just as RCO3H. That's fine. Sometimes you'll see it written more specifically as a particular peroxy acid. Probably the most common is this MCPBA. You might see that as well. Peroxyacetic acid is just the simplest peroxy acid with just one methyl group here on the R is just, any of these are ways to write these. I usually write it this way, but sometimes your book will specify MCPBA specifically. When it comes to epoxide reactions, they're going to have a kind of stereochemistry to them, right? When it comes to the addition here, the addition when you're making the epoxide, essentially you're getting a bond from each of these carbons to the oxygens. So wherever your groups are positioned, like here where the two R groups are on the same side of the double bond, they're going to end up to the same side in terms of the stereochemistry. So here they're both drawn on wedges in this way. Whereas if they're opposite side on the double bond, well, they're going to end up on opposite sides of this bond. So if one is a wedge here, the other will be a dash. So the stereochemistry here is preserved in a sense, where if you have a cis alkene, you end up with the ring with the two R groups on the same side. If the alkene's trans, you'll have them on. You can also make epoxides from halohydrins. So you may recall that we made halohydrins in the past by reacting an alkene with an acid and water at the same time. And so the water ends up being the nucleophile here to attack after the protonation occurs, and so you get this halohydrin formation. And if you expose this to a strong base, you can make oxide with it. The way that works is the base here deprotonates the alcohol, and so we have a proton transfer. Usually, the hydroxide isn't the perfect base to deprotonate an alcohol because water is not significantly more, if you're talking about water, the protonated form, you may recall the pKa was 15.7. And for the alcohol, the pKa, so ROH, the pKa is going to be around 18. And so the water is more acidic than the alcohol, but you'll get some deprotonation, which is enough because then you can, this will engage in a nucleophilic attack as long as these are on opposite sides of one another. They have to be anti, so they can be anti-periplanar. And in that case, we can see, well, it's not like an elimination, but this opens basically the pathway for the epoxide to react if they're anti in this way. And then at that point, you have the epoxide. So, and this removes the epoxide, so it's not as big of a deal that not a lot of these were deprotonated, because then this will be removed, and then the next one that's deprotonated undergo this reaction. So notice that either way we prepare these epoxides, either directly from the peroxy acid or by taking the alkene and doing a, whoops, I said HBr, I meant Br2. My apologies. Sorry about that. Br2 and water followed by a alcohol here. You can produce, either way you're going to produce a epoxide in which the stereochemistry. So at this point, I'm going to end this part of the lecture. In the next part of the lecture, we're going to talk about, now that we know how epoxides can be formed, either through the reaction of an alkene with a peroxy acid or an alkene with a halohydrin, Br2, not HBr, and water, followed up by a strong base, sodium hydroxide. After we've made the epoxides, what can we do with them? Well, they're highly reactive, and we can use them as nucleophiles, to react with nucleophiles. We can use them as electrophiles. Um, and so they can react with nucleophiles like Grignard reagents, hydride, alcohols, alkoxides, and so forth. So we're going to see how these epoxides will react with nucleophiles. They will be the substrate in a nucleophilic substitution because that ring opening is just so easy due to the ring strain. We'll talk about that, then we'll wrap up by saying a few things about thiols. And I'll see you in the next video.